start, I think, at 10:30. There's a coffee break going on at the in-person PLDI conference, so we'll probably wait for that to finish and then get started in 5 minutes.
Looks like this cabling might leak.
Check. Check. Okay.
Can you hear me? Can anyone hear me?
Can anyone hear me?
Yes. All right. Hello, everyone. Welcome to the first session of ISMM 2020. My name is Martin Maas. I'm a research scientist in the Google Brain team and a member of the ISMM steering committee. And I'm very excited to start this conference off with a panel. Our panelists are Christine Flood from Julia Computing, Chris Cannelly from Google, and Wes Filardo from Microsoft. And this is normally the point where I would introduce all of our speakers, but they'll actually do that themselves. We'll start off with three short talks where our three panelists will tell us about their work. And after that, we'll dive into Q&A. I would say let's do it in this order: Christine, Chris, and then Wes.
Okay, I'm having network connectivity, so I'm not going to show you my picture. I'm Christine Flood. I work at Julia Computing. I've been doing a lot of programming language runtimes for years. I've worked on Lisp and Java, and if you've heard of Fortress, and then I worked at some for Java and some for Fortress, and then I went to Red Hat for Java. So if you've heard of Shenandoah, that was my project. And now I'm at Julia Computing. So what does Julia Computing do? This is the one professional slide I have. We do really fast differential equations. We have a language and a community for the language, and then we have a platform built on top of it, which is where the money comes from. It's a cloud computing platform, Julia Hub, and then on top of that we have circuit.
So it looks like we have some connectivity issues. Christine, can you hear us?
Can you hear me now? Or should I?
Yes, I think we can hear you again. We lost you for a couple of minutes, I think.
Okay. Julia Hub is really cool. Oh. Julia Hub is for compute cycles. You can call out to LV to change the way things are. Which compared to Java is wonderful. You used to have to know magic incantations. Here you can just see what the native code compiles to, what the LLVM instructions are, what the types are, the type. Everything is transparent. We also have an enthusiastic community. So I'm going to be really quick with my introduction because this feedback is driving me crazy. Memory management in Julia is precise-ish. We only have a minimal root set, so if you wanted to do a compacting garbage collection, you couldn't do it as it stands right now. We're non-compacting for that reason. Nothing moves. We are generational, and we have marked sleep. And we've got some efforts going to make it better. We want to parallelize it. We want to do mostly compacting, which is anything that's put into by the root set stays, and anything reachable from inside the heap can be compacted. And we want to add age bits to give things longer to die in the young generation. And the issues that keep me up at night, memory is now cheap. Most of my garbage collection work has been done on heaps of hundreds of gigabytes and hundreds of megabytes. We're looking at hundreds of gigabytes. So the question is, have we outgrown old generation collections? Is it just not feasible to spend the time to walk over hundreds of gigabytes? Reclaiming resources like file handles or GPU memory depends on garbage collection, but garbage collection is only triggered based on CPU memory pressure. So folks want to be able to have GC do the work for them that it wasn't intended to do. And so how do we figure out how to make all that work? Users are getting more savvy. They align their data to perfectly get optimal cache performance. And GC, especially parallel GC, interferes with that. And how Julia interacts with foreign functions and passes objects back and forth. In Java, that would have been, J and I, but nobody really likes J and I. So how do we?
So, Kristen, I think you're still dropping in and out, but all right. Kristen, are you done with your presentation?
Yes, I am. I apologize.
Oh no, it's connection problems. It's the first hybrid ISMM, so we're figuring all these things out as we go along. Thanks so much for the presentation, Kristen. So now we go to Chris Kennelly. Go ahead, Chris.
Hi, I'm Chris. I'm a principal software engineer at Google, and I hope that, okay, thanks for muting. And so I work on improving the efficiency of our software stack. And one of the things that this entailed was getting involved with memory allocation. About 7 years ago, Google published a paper profiling a warehouse scale computer where we looked at everything and we said, TC-Malloc is 8 or 9% of all of Google's computing needs, which was staggering. And then immediately led to questions of, can we do anything about it? And so we started optimizing the implementation of TC-Malloc over and over again. And so, can we shave off a branch here or a memory load here? This was very successful. But then as we ran out of those kind of opportunities, we started looking at a bunch of other areas of, okay, can we optimize memory fragmentation or can we optimize placement? Because rather than be singularly focused on, let's speed up the cost and time it takes to do malloc and free, we can switch over to, we'll do different decisions for malloc and free. They might be nominally more costly, but the whole application will speed up to offset that. and pay for the additional intelligence we put into malloc. And so our first foray in this was a paper we published a few years ago, last year at OSDI, called a huge page aware allocator that we had called Temeraire. So we were able to say, let's think about how to do placement at a huge page level and huge page bucketing and deal with the fragmentation problems that can entail, rather than just naively place memory pages and allocations onto memory and find out that we weren't being very huge page aware and kind of getting the worst of all worlds from, when do we release memory to the OS and we break up our huge pages? When are we putting things close to each other? Because like, even if I have perfect huge page coverage, if I've scattered allocations all over my address space, I still will have poor TLB locality. And so we did all those things and built a new backend for tcmalloc, and we're able to improve application performance considerably while reducing the actual TLB misses we were seeing and memory usage and overhead just sitting in malloc, because rather than have to be really conservative about releasing memory, we could actually be even more aggressive. That has then turned into a bunch of other kind of spin-off projects. One is a paper Martin and I co-authored about figuring out what is the right time to release memory. A lot of people will look at tcmalloc and say, hey, I'm holding onto a bunch of memory that I really don't want to. Let me turn up my release rate. And the release rate goes up to 11. But we ended up finding a lot of applications kind of just oscillate back and forth. And can we make smarter decisions about holding on to it for a short period of time, because that smooths out a lot of troughs in demand that are short-lived. But I think kind of looking to the next areas of malloc that we're very interested in, or at least I'm very interested in, is, can we keep making things smarter around placement decisions? Because, okay, in C++ we don't get the benefit of moving GC for the most part, unless you do clever tricks. And can we find places where we can blur information a little bit more of, the application can tell us something, or the compiler can tell us something, or we can tell the kernel something, because this is where we've been pretty successful at blurring lines of abstraction, because it lets us improve efficiency. tcmalloc was named tcmalloc because it had thread caches, but we now have per CPU caches because we were able to blur the line between the kernel and user space a little bit to have it tell us and give us a primitive that we could actually build these sort of data structures with. So overall, I think that's been the main focus of how do we improve application performance, and a lot of that comes from thinking about tcmalloc or other libraries, but also finding ways where we can have the two tcmalloc cooperate better with all the other parts of our stack. If we can get one library to use tcmalloc more effectively, or coalesce its allocations or tell us something about them, we can use that to improve our placement decisions and thus application performance. Those are my brief introduction of where I'm coming from in malloc. I'm happy to pass it on.
Thanks, Chris. And last but not least, Wes.
Hello. So hi, I'm Wes. I'm a senior researcher at Microsoft Research in Cambridge, and I work on, first off, you can hear me, yes? Great. I work on memory-safe architectures and kind of up the software stack. So of course, one of the first things you run into is malloc. So without getting into much in the way of details, what do I mean by memory-safe architecture? I just mean things that can give you C and C++ pointers that can't be dereferenced out of bounds. So historically, there are a bunch of things that kind of look like this. The one sort of modern contender is Cherry. But the key point of all of these things is that they give you exactly what they say on the tin, the notion of pointing somewhere and bounds around that somewhere. And those bounds have to come from software. Of course, the canonical place that bounds would come from is your memory allocator, so malloc. So what's the problem, right? Malloc takes a length, just set the bounds to be that long on the way back to the application, and you're done, right? Well, unfortunately, not so much. So when writing a memory allocator, right, two very popular heap layouts that we see in practice are to put per object metadata in a header next to the object, or to kind of group together the metadata of a whole bunch of objects at some conveniently aligned granule. So, you know, every 16 megabytes in your address space, you have a chunk of metadata that describes that 16 megabytes. But we just said that we have a way of expressing pointers that can't be used out of bounds. And here we are taking pointers and computing addresses that are out of bounds to access metadata. So we can't do this anymore. We have to reach all of our metadata via allocator private state. So globals or thread local storage, or in APIs where you pass a handle in, you could use that too. This is not a problem. Sorry, this is not just a problem at the allocator application interface, but it is also a problem within the allocator itself, especially if you have anything that looks like a front-end back-end separation, or you have a consolidating allocator. Basically, anywhere that you need to go from a collection of objects with their discrete bounds to a single pointer with all of those objects in bounds, you have this problem. So in SNMalloc, the way that we solve this is that we use a what we call the page map structure. It's a map from every 16 kilobytes of the address space to per slab or per large object metadata structures. And it is a very convenient place to store pointers with wide bounds, right, to the entire slab or even to the entire allocation arena if we need to. This structure was introduced not just for Cherry reasons, but it does make our Cherry implementation much easier. So, okay, this means that we can go both ways, right? We can take a pointer that it has bounds of the entire allocation arena, and we can whittle that down to ultimately shipping out a pointer to the application from malloc that just has bounds of the one object. And when they pass it back to free, we can jump back through this page map and find the pointers with the appropriate bounds for the operation we need to do. Great. But in high-performance allocators, you frequently have your slow paths do a bunch of work to speed up subsequent fast paths. And in particular, you cache a whole lot of pointers internally. So you build free lists optimistically, or you build local cache, or thread local caching. So when we are bounding a pointer to go out to user space or to the user application, we need to make sure that either we have set up the cache correctly, or we will set up the cache correctly when we subsequently pull from it. And if all of those are just void stars, as is kind of canonically the case, it's really hard to tell and be sure that you've gotten all of the bounds right and that, you're not missing something. So the question then is, can we do better? So SNMalloc made the possibly curious design decision to be implemented in C++ rather than C. But this, for present purposes, this means that we can use the C++ type system to guide the reader and software author. So we introduce a simplified static bounds ontology. So this isn't a dependent type system. We're not actually tracking the real size. But we're sort of giving a schematic role of what we expect this pointer to be. Is it a pointer to the arena, to a large part of the arena, or to a particular allocation? We use a capputter TB type everywhere. This is just a pointer to T with bounds B. And throughout the code base, we have like safe affordances as primitives for doing the right thing. Right? Of course, you can all just cast it away, but ideally, you use the affordances we give you. So for example, the function that applies bounds to a pointer will statically constrain that the input bounds and the output bounds are in the right direction. You can only narrow bounds. You can't take a narrow thing and claim to be rederiving a wider thing. And then the last function that we call on all of our allocation paths is this capputter reveal, which constrains its input type to be alloc bounded. And so this guarantees statically at compile time that whatever pointer flows into that point has gone through something that at least claimed to be the right bound setting. And in practice, then all of our like proto-allocation pointers, the ones that will give rise to things that we ship to the user, are these cap putters. There are actually very few void stars floating around internally. Okay, that actually does pretty well for spatial safety, but memory safety has also temporal aspects, the canonical problem being use after free, where you allocate something, free something, hold onto the pointer, and use it by mistake. In order to fix this, in order to enforce temporally safe use of heap objects, we need to eventually, as the C standard would call it, convert P to be a trap representation. But what does that actually mean? How do we change a pointer that we've already given out to the application? Well, there are two things we can do, and we have research in both of these. We can change something about the target memory to invalidate all of the pointers to it. Or we can change something about all of the pointers to the allocation. We can actually go find all of them and do something, like, say, replace them with null. So maybe the most exciting research bit of this is memory coloring. So this is basically a composition of Cherry spatial safety with ARM MTE or Oracle SSM or ADI, that's the one. But the short of it is we kind of tack onto the side of every 16 bytes of memory 4 bits of color, and then we stick 4 bits of color in every pointer in the system, and they have to match for you to be able to access memory. So when the allocator, which has authority to access the entire heap, when the allocator goes to ship a pointer out to the user program, it will color that region of the heap and make a capability of a matching color, so the application can use that. When the application frees that allocation, the allocator then uses its elevated authority to immediately recolor that region of the heap, which invalidates that capability. The client can still have it, they can pass it around, it's still the same pointer that it was, they just can't use it anymore. And eventually, when it comes time to reuse that piece of memory, the allocator can mint a new capability with a different color that now matches the recolored heap and give that out. There are architectural primitives that prevent, or aspects of the architecture that prevent the untrusted client from switching the color in a capability or changing the color of memory. You need one of these rainbow capabilities to repaint things. So what this looks like ultimately is the allocator will allocate memory with constrained bounds and color, a particular color. When the application calls free, we will recolor the heap and we will decide whether or not there is another color available. If there is, we are clear to immediately reuse this memory. We can even put all of the in-band metadata we want in place to, for free queues or whatever, and we have to do no protection on, or whether we don't have to do any protection on them because they're inaccessible to the client. That's great. If we run out of colors, right, there are only 4 bits, we do eventually count to 16, then we have to quarantine that address space. That is to say, it doesn't go back on the free list. It instead goes into some shadow region. And eventually, we will find that either we're running out of address space, which on a 64-bit machine happens very slowly, but we might find that we're running out of address space, or that the address mappings are sufficiently fragmented, right? We've got too many pages with very few things on them, that we really do need to go run this global revoker to shoot down all capabilities whose color does not match the thing that they point at. This is expensive, but tractable. We have an implementation from 2020 that wasn't using the colors, but was just doing a sort of 1-bit version of this that had reasonable, like 10% kind of cycle overheads. And there's some caveats to that, as there are always with benchmark numbers. But the coloring scheme will let us run that a 16th as often, which is pretty cool. So to recap, memory-safe architectures seem like things that they are possibly actually happening in the ecosystem again, maybe for real this time. And we would like to build memory-safe C and C++ on top of them. So the questions then for memory allocators are, how do we amplify the bounded pointers that we've given out to existing mitigations are still compatible with this. You can turn them on if you want. Temporal safety is an active area of research at MSR. But the big questions, kind of backing up a little bit, the big questions for this community, for systems researchers in general, are things like, suppose that bounds, invalidation, and verification are actually just available architectural primitives, right? What more could we do? Are there moves we could make that would be very useful? For SNMalloc specifically, but also this design of coloring and revocation, right, is there performance that we're leaving on the table? Are there other designs that would work better? And then last, are there attacks or issues that we have overlooked? And I think that's it for me.
All right. Thank you so much, everyone. So we now have about half an hour to ask questions to our panel, and it looks like we have a crowd virtually. We also have a crowd in person at PLDI over here. So what I would say is, let's do the following. I'm going to start off with a couple of questions, and I have more questions if we don't have any questions from the audience. But if you're virtual, please step up to the little podium and gather. And if you're here in person, okay. Okay, let's try again. If you're here in person, please queue up in this area over here, and then you can step up to the laptop and ask questions directly. And let me see whether I can make this a little bit larger. All right. So I'll start off with the first question. So the theme, I think that came through all of these three talks was that requirements of memory allocators change. Sometimes the properties that you want to achieve change. Maybe you want more security. Sometimes the workload change, and memory allocators have to evolve with it and target these kind of specific scenarios. So this is a question to all three of you. Where do you see the next change in requirements? What are the areas that will become important in the future?
CSMA is a fun protocol. So why don't I take a stab at that? So the thing that I see coming, not as a hardware architect, but like as a software person sort of looking at the field, I wonder how long it's going to be that we can maintain cache coherency. So sufficiently large systems where single address space is not a credible story. So we then have to, we have to teach our allocators that these are shared objects, but are temporarily resident in particular nodes. How do you copy things around? I think that this is going to be a big change to the API with consequential, basically, rewrites of the whole world.
Chris, do you want to go next?
Yeah, I think like even before you get to a lack of cache coherency, I think just even NUMA locality or NUMA-like properties, or you see this in other different cache architectures, where malloc from one place is not equivalent to malloc to another place, simply due to you're running on a different NUMA node or other NUMA node, or you have a shared L3 or a non-shared L3 between your two cores. And I think while we have this abstraction around malloc gives you some bytes to play with, it's something that users have to be very cognizant of, as this, the abstraction can only protect them so much from the hardware and the underlying heterogeneity of it.
I would agree with you. That's an issue that is already serious in the face. But also distributed memory. You have memory in GPUs and you need to get back and forth. It manages the memory on the GPUs. And as far as
So continuing on that theme, I think NUMA is one area of this kind of heterogeneity. I think as Christine touched on, accelerators, I think, are another such area. Do you all think that memory allocators need to do something different in the presence of accelerators and distributed like memory across these accelerators, for example? And if so, what? Maybe start with Chris.
I mean, I certainly think that some of that would be, yes, we'll have to do things differently, but that might just be we solve the problem in a different way of allocating memory differently rather than it being the one-size-fits-all of you call malloc and you're off to the races. You'll need to manage memory more explicitly for I need to interact with a hardware device or the network card, and I think that's slightly worse ergonomics, but necessary from a, we can't really have a one-size-fits-all of you call malloc and free and everything works, or at least works just as seamlessly. There'll still be some abstraction of I need to pin pages for upcoming DMA and then unpin them when I'm done to let the kernel continue to manage them. And that might just merit having a dedicated allocator for this purpose of interacting with this hardware subsystem.
Maybe Wes next.
Sure. So there's been some work sort of tangentially related to this in SNMalloc already. The SNMalloc is in some sense a fleet of allocators in a trench coat. It has a per thread, not just cache, but essentially complete allocator. And freeze in particular, so if thread A allocates something, passes a pointer to thread B, and then thread B calls free, that goes into I think that Matt called it a temporal radix tree. It's basically a cached message passing structure that ultimately passes that pointer back to thread A to deal with. And so it happens that per POSIX thread, you have one of these allocators, but if you want, you can just conjure up another one for whatever purpose. And then it's, as you said, it's, as Chris said, it's slightly worse ergonomics for I have this special purpose allocator that I need to use, but at least it plays well with the rest of it so that I could say allocate something in GPU memory, but that pointer can go to any free anywhere in the system, and it will make its way.
There are questions in the chat as well.
Let's see.
There are some questions in the Slack channel.
In the Slack channel, okay.
If you want, I have them on my phone. You can read them off.
Okay, let's do the following. We have one live question, and I'll read up on the Slack channel, and then we'll take questions from the Slack channel as well.
Hello, thank you for the talks. So my question is about kind of the role of type systems in the development of memory systems and languages like Rust. So I am kind of broadly wondering how, with the existence of a language like Rust or Zig or any of these sort of burgeoning systems languages that have maybe more static knowledge about the semantics of the program, when things get allocated or deallocated, about what permissions exist for different parts of the program to touch pieces of memory, like how, for a world that solely existed within a sort of, say, like a Rust consistent way, and there was no unsafe FFI, if that was even possible, do you think that could be used to make these allocators more efficient, either by reducing the amount of dynamic tracking that needs to happen, or by, say, batching up allocations in a different way, or just more generally, if you have any interesting thoughts on how to take advantage of these, increasingly advanced static type systems to improve the performance of the memory allocators.
So I can take a crack at that. I didn't talk about this in my slides, but SNMalloc is in some sense a spin-off of another project called Verona, which is a Rust-inspired, or if you like, Rust on steroids language, where we're using the type system to give us not just sort of single pointer ownership, but entire region-based ownership. So we can, within a region, we can build cyclic graphs because we know that all of those objects are part of the same region. And it's only the only acyclicity requirement a la Rust is between regions. But then into that infrastructure, we can hook things like arena allocators. So you can say, give me a region, all of whose objects have the same endpoint of lifetime, right? They might be created dynamically, but I promise that there is a point in time where they will all go away. Or this region needs to be GC'd, but it can point to arena allocated things, or so, right? So you can really mix and match along the region graph the allocation strategies that you want. I think that indeed will be really, really powerful. Still a little bit in development, but it is open source on GitHub if you want to like look over our shoulders or join us.
I think the type information is also, in addition to just the arena and the lifetime bounds that Wes mentioned, I think is also, can we remix allocations in exciting ways? Like, do we have to have it be one contiguous allocation? Or, I have a data structure, can I reason about, I could split off parts of it and make that two logical allocations of like, I have some very frequently accessed things and I have some less frequently accessed things that I want to segregate in address space. And the other would be, like, one problem we have with TCMalloc has always been like, we can't move an allocation from someone. But if we know enough about the type system and how memory is actually being used, and that you didn't take a pointer and stash it, XOR it with some random number and stash it somewhere that we can't see, can we use that information to move an object? And that might require a little bit higher knowledge in constructs than simply the type system. But I can take a very long-lived thing that's causing problems from a memory fragmentation standpoint and maybe try to work with the other layers of the stack to say, I want to move this. And we know we can do so safely because we can reason about it. And I think that's where a general purpose malloc doesn't work, but where additional information can be really helpful because it lets us do things we otherwise aren't capable of.
I'd like to take a try, and hopefully you can hear me. I am new to Julia, so some of these things are new to me. And one of the things is that objects by default in Julia are immutable. And what that means is a lot of the time, and a lot of types, don't actually have a heap representation. They're actually just slots in the stack. And from a garbage collection perspective, which is where I come from, that's amazing. Because now the garbage collector never gets involved at all.
All right, great. Thank you for the answers.
Thanks, everyone. We have a question on Slack. So you are working in industry. What are some good benchmarks used in industry? Are micro benchmarks used, or is the focus on testing on live applications? Let's maybe start in the reverse order and start with Kristen this time, and then Wes, and then Chris.
I can speak for Java authoritatively and Julia a little bit. In Java, we had both sets of big benchmarks that came from customers, and we had micro benchmarks, and we had medium-sized benchmarks. In Julia, we have micro benchmarks that get run every night automatically. And I've been working with folks to develop a set of memory management benchmarks that they're artificial, but they test the kinds of things that we want to test. when we're trying to get performance improvements. And we also have the ability, which is really amazing to me coming from the outside world, to run all of the Julia code on GitHub and make sure that it still works with a controversial change. So we can do it all, but we don't do the last one very often. At least I have never seen it done.
Wes?
Oh, sorry, I guess it's my turn. So embarrassingly enough, for the little bit of the research org that I'm in, we mostly stick with spec and just look at how our changes have impacted that. They're not great, right? That's not really the right thing to do, but it is at least a standard thing. And then a lot of micro benchmarks when we see, oh, we could change this, or we will come up with a little thing that just exercises that and see how much faster we've made it.
So our usage of micro benchmarks has been fairly limited just because we can't realistically simulate access patterns with it. Like we can find out how fast malloc and free are and try to shave off of cycles here and there. But for I want to change a placement policy of how I bin pack allocations onto pages, or how I place those logical pages onto physical address pages like huge pages. We don't have good models for that, so most of our reliance has been on taking performance-sensitive macro benchmarks, using those to get a general sense of direction on a change. And then the other thing we've been able to do is enable on a broad swath of systems in our data centers, can we enable on 1% of machines a different behavior in our memory allocator? And at that point, we generally need to have a fairly high certainty about the robustness and general performance of a change, but it lets us put much finer calipers on. Can we see there's this outlier behavior in a limited scope, rather than we roll out a change and find out this application doesn't work at all with it and kind of requires a rollback because the performance is just too catastrophically worse. But it lets us see the behavior at wide scale without necessarily having a ready to go, accurate representative benchmark from every single team that might use TC-malloc. And that's how we've gotten a lot of data to be able to make changes to our allocator and move forward.
Thanks, everyone. We have another question from Slack. Once again, I want to encourage people to ask questions. Oh, we actually have a live question as well online. Why don't we start with Michael, who's at the microphone right now?
Hey, let me try it this way. I actually also posted a question on Slack, so I'm just going to repeat it here now. So there's a question for the allocator people mostly, I would say. Thanks for all the presentations, and I see there is actually, it feels like there is appetite for specializing allocations, like for performance and security reasons, leveraging the type system. Looking at what we do or industry does with these very large code bases, it feels like there is need for different malloc APIs. And I would really like to hear your opinion about this one, because it feels like everybody, and I'm talking like saying this in a broad context now, but it feels like everybody is bending over backwards to get the information that may already be out there and users may actually already know. But it's just impossible to run these generic programs that just call malloc on our big fleets and determine what's actually going on there.
So Chris, why don't you go first? Chris, Wes, Christian.
Martin, do you want to pick an order?
Yeah,
I'm happy to talk, but you're muted.
Oh. Can you hear me now?
Can't hear you.
Okay.
I can. This is amusing. Eventual consistency for the win.
Hybrid conferences are exciting. Okay, so let me type this.
Okay, now I can hear you now.
Okay, so Chris, why
Okay.
don't you go first? Then Wes, thank
I mean,
you.
I certainly think malloc is definitely not a good API. I think there's a long history of adding more things. I think starting with, and again, I think I come from mostly a C++ focus, and I think it'll show in my comment of like C++ 14 added size delete. And it looks like C is going to add a sized free in the next standard as well. And here's where we can give a little bit more information that the compiler or the type system generally already knows about a call or to free or delete and can pass it along. On the converse of that, one thing we have prototyped in tcmalloc and I've been working to get into the C++ standard is, can we tell you how big our allocation was? Because we know the answer, and you might be able to use that extra free space rather than do an extra reallocation. But I think there's also a bunch of other things around, lifetime or hotness over that object's lifetime that let us change our placement decisions in ways that we can't do if we had to predict a priori from you called us with a given size and maybe we took a call stack and made a prediction from it at runtime, because you might have a better sense of, you have a data plane that all objects get allocated through the same point, but some objects have a longer life from there or shorter life, or get accessed more or get accessed less. And I think those are areas where additional ways of passing that information can help the allocator make better decisions.
Yeah, we like 3-4 years ago, when we started down this path of like, can we do revocation on Cherry? We had a slightly different architectural model that meant that it would have been very, very nice for us to have contiguous swaths of the address space all in quarantine, right? All that needing to be revoked. And so we set out to measure, here's a trace of malloc and free. What are the lifetimes of objects and how well can you predict it just from the size and the program counter of malloc? And I won't say that there's no signal there, right? But like it varies by application. And the worst thing is that you find wrappers of malloc. So, right, the most common functions to call malloc are my_malloc. And that just paves over your ability to tell anything. So I think, yes, we need a new malloc API. I think it's vitally important that we be able to pass lifetime and Chris's point about hotness information into the allocator so that it can do a better job with layout. Unfortunately, that's going to bring with it the cost of kind of plumbing that up the stack and like undoing all of this encapsulation that has been done and like specialization of malloc that has been done over the years.
I think the other flip side I'll add of specialization is just then we can be wrong in a new way. That's even more exciting.
If we knew what we were doing, we wouldn't call it research.
Yes.
Kristen, do you want to add something?
I'm a consumer of malloc, so I don't think this question is directed at me.
All right. So we have one more question that kind of ties back to something that was brought up earlier. So given that benchmarks are tricky, is there a need to develop a new memory management benchmark suite, given that workloads have changed? We heard that in all 3 talks earlier today as well. Kristen, do you want to start, and then Wes, and then Chris?
I think benchmarks, we always need more benchmarks.
Yeah, I think I'll just echo that with more benchmarks would be better, but please don't ask me to design one.
I'll also throw in a third of more benchmarks are better. I think the big question would always be knowing the limits of where it is or is not representative. And if we invest a bunch of effort in, say, I embark in building a benchmark modeled based on some higher level, more complex workload. By the end of that journey, do I know if it's still representative of the workload, or as we said, things have changed? And so being able to validate that it has the same access pattern or composition against some other thing that I'm trying to model or simplify is really useful for giving a boost of confidence of this is something that we should worry about, or is this something that it's a proxy, but it has some downsides and caveats, and we should keep those in mind when we're trying to fit to it.
All right, we got one more question on Slack. Does security of memory allocators rely on composition of disparate architectural features? Can provide partial security guarantees? Can we provide partial security guarantees with partial feature coverage? So, for example, is malloc security compositional, or more generally, are allocator features compositional in nature? So I think this is probably a question for Wes. So why don't we go Wes, Christine, and then Chris?
Sure, I can take a stab at that. So I think that there is indeed a spectrum of options that you can explore, with the one end being just no support for undefined behavior is indeed undefined, and on the other end, all undefined behavior is guaranteed to trap immediately, and you can build along that path. So even early on in allocators, right, we saw things like electric fence where there were clever page tricks being used to catch out of bounds references of allocations or catch use after free. That tended to come with such high costs that it was only used in debugging, but it was a real effort in finding a point on that spectrum. The current, another point in the space is the current SNMalloc mainline is able to take advantage of cherry for spatial safety, but is running without any cherry protections for temporal safety. So it is doing randomized reissue, and it is doing some pointer signing kinds of tricks to check that you haven't corrupted its free lists. But it is sitting in the middle of that space where it has adopted some architectural features where it can and is falling back on other mitigations where it can't.
Kristen next.
I don't have anything to say about this.
Chris, do you have anything to add?
I mean, I think it's a trade-off curve of and I think Wes touched a bit on this, of we can layer multiple defenses at different costs and have a different probability distribution of detection of a problem or a class of problems. And I think that's something to keep in mind from a security perspective of how much you might want to harden an allocator versus you believe the code is actually correct because it's been extensively tested and fuzzed and used. And that might require a different set of guarantees than you need from all possible layers of defense if they come at a high cost to performance or the overheads of the system.
I think just to amend my answer a little bit, the word compositional is really interesting, right? I think it's certainly true that whatever point in the space you end up on is composed of constituent features. But I think, at least to date, moving in that space from one configuration of these things trapped, these things are probabilistically caught, and these I will let slide without catching, moving to another point in that space has generally required pretty invasive re-architecting of the system software, including the allocators. So I think that a challenge with security, especially the red teaming people are just very, very good at, if you give them a toehold, they will take over the entire system. And in that kind of a space, it's very hard to reason about orthogonal features or to treat features orthogonally. You have to really think holistically about the resulting design. If you have a way of changing that, I am all ears.
Anyone wants to respond to the last point? Sounds like a good discussion for one of the breaks. Before we wrap up, I have one last question for all speakers. So we have a lot of students who are looking for new topics to work on. So which areas of memory management would you like to see more work in? What if you were making a recommendation to students what they should work on, what would it be? And why don't we start with Kristen, then Wes, then Chris.
So, my biggest problem that I don't know how to handle is that when you're running a garbage collector and you have a large amount of static data, it's becoming unfeasible to mark that data. So if somebody can come up with a sort of a remembered set representation that is not too large, that can tell me that this stuff is here and it's staying here and these are the pointers out of it, that would make my life so much easier. And if I can only look at updates when they happen. So some method of managing tenured space that doesn't require marking and sweeping and that preferably works a little bit better than reference counting in terms of overhead on the compiler. That would be what I would love to see. I don't know how practical it is, but you know, I'm asking for the moon. And otherwise, how to interact between the CPU and the GPU, and to have the memory management work together. Oh, and how to have the garbage collector not mess up the cache.
Right, I think Wes is next.
Oh, okay. So yeah, the thing that leapt to mind was the thing that Christine just said at the end. I want to change how software and hardware interact. I want the kernel out of the data plane as much as possible. I want to share virtual addresses, and in fact, I want to share capabilities with hardware and know that the hardware will be constrained by those capabilities. But this means, this necessitates replumbing basically everything from the CPU front side bus out, right? We need to pass capabilities attached to their address spaces around in DMA engines, kinds of things. So I think it's a really, really interesting space, and I don't know what the solution looks like.
I think the most interesting area for me is, finding more places where we can blur the lines of, we talked about malloc and the layers above it and layers below it, but where we can blur those lines in new ways that we haven't thought of yet. Since we haven't done that too many times, but I think there's a whole wealth of information that we can pass from one layer to the other that gives us a lot of potential research opportunities for finding new benefits from doing so, whether that helps security from type system and lifetime information, or helps performance because we have a better sense of how things will actually get used, and we can do better placement either in address space or on the physical hardware accordingly.
Thank you, everyone. And I think this brings us to the end of the panel. Please feel free to post more questions online or find the speakers and talk more to them. Thank you so much, Chris, Wes, and Kristen, for being on the panel today and for the really engaging discussion. I hope this starts some interesting conversations at the conference today.
Thank you for the invitation.
So we're now going to dive directly into the first talk of the conference. This talk will be given by Shay Bergman. right. Shay is a PhD. Hello. Shay is a PhD student at Technion, and he's currently at Imperial College London. And he'll be talking about disaggregated memory.
Thank you for the introduction. I think I need a place one of the two spots